actually deals with the metric on Kähler metrics on modular spaces, which I think is appropriate with the title of the conference. And moreover, there will be analytic aspects of the metric geometry of modular spaces, and also the organizers in the email asked me to pose some questions. I'll do. So there will be also questions in this talk. So this is the plan. So we'll basically, the first part will be a review of basic metric properties of the modular space of punctured Riemann surfaces. Then we'll discuss potentials and Chern forms on special modular spaces of type of genus 0 Riemann surfaces. Then we'll introduce the Schottky space of genus G with n marked points. And then very briefly, I'll discuss renormalized volumes for this part. So, and we'll start with a very brief overview of the complex geometry of the modular space. Well, there are many equivalent definitions how to define and introduce a complex structure in the modular space. This is the most traditional, goes to Alford Bears. So I will use complex analytic. And this also fits well to the deformation theory of Kadeira Spencer, and like André Weil, he developed similar approach using the same objects. So we'll start just by reminding. Basically, this is to fix notation. So we'll start with the genus G Riemann surfaces with n punctures, marked points. This is the modular space, is a complex orbifold with this dimension. This number is assumed to be positive. Then what we like to do, we'd like to characterize holomorphic tangent, this is and cotangent spaces to the modular space. This basically will be a crash course in deformation theory. So in a nutshell, the holomorphic tangent space at a point, which is represented by a Riemann surface X, is a complex vector space of harmonic Beltrami differentials. Harmonic means that this harmonic with respect to the hyperbolic metric on type Gn Riemann surface. So we consider Riemann surface with punctures. Then there exists a unique hyperbolic metric. You consider the infinite dimensional space of Beltrami differentials, and then according to Hodge theory, there exists a finite dimensional subspace of harmonic. That's what we'll do. This was introduced by Bears, essentially. This sometimes is called Bears harmonic. Then holomorphic cotangent space can be identified. Of course, all of this is identified with a complex vector space of meromorphic quadratic differentials. In the case of punctured Riemann surfaces, they are allowed to have simple poles at the punctures, at most simple poles. So these are the complex vector spaces of the same dimension, and the natural pairing is given by integration. And so just to and effectively, if we uniformize our Riemann surface as a quotient of the Lobachevsky plane, the hyperbolic plane, by the action of a torsion-free Fuchsian group of type Gn, then corresponding meromorphic quadratic differentials correspond to cusp forms of weight 4, and correspondingly harmonic Beltrami differentials have this form. So there is complex antilinear isomorphism between tangent and cotangent spaces. So that's very brief reminder. And just to make it a true deformation theory, we need to show how to integrate, how to come from one surface to another nearby. This is done by elliptical engineering using Beltrami equations. So that's all. Now let's discuss the metric properties. So the Weil-Petersen metric was introduced by André Weil, and is given by the Petersen inner product of two tangent vectors. Explicitly, you can integrate, take this product of Beltrami differentials. It's a function on a surface, and then you integrate with respect to the hyperbolic area element. Or using the uniformization, this is precisely Petersen inner product of cusp forms of weight 4. So that's why it is Weil-Petersen. And then the basic facts, very basic, fundamental facts about Weil-Petersen metric are the following. It's scalar and has negative Ricci, holomorphic sectional, and scalar curvature. The fact that the metric is scalar was proved by Weil. He has no paper written on it, but there is some report. I think he had a grant from Air Force or from the Navy, and where he did the deformation theory of the modular spaces. And he said that he did, well, you can read what he said. Yeah, it's interesting. I won't say it.
There are also notes of his in the Princeton Library.
Right. And also there is a Bourbaki seminar, I think, where this, but he has no published paper on it. And then, so Alfors, in his classic papers, proved this result, and then Scott Wolpert obtained explicit formula for the Riemann curvature tensor of the Weil-Petersen metric using the Green's function. The Green's function is the resolvent kernel of automorphic Bertrami Laplace operator evaluated at a certain point. And the formulas are explicit using the Green's function, and then one can, from these formulas, one can prove much more. One can get explicit bound for curvatures and other things. So these are fundamental facts about Weil-Petersen metric. Then it's properly normalized. It's a rational class, non-zero. Then, if we talk about Kähler potentials, one needs to consider certain covering spaces of the Riemann modular space. And there are two. There are several interesting examples. One is if you consider the simplest case, the modular space of genus 0 Riemann surfaces with n punctures. Another case, you consider modular space of pointed rational curves, which is a manifold. And then it has a nice cover. It's just a configuration space of n points. And then on this cover, one can actually, this becomes a zero class, and one can get some interesting potentials using classical Liouville action, using some ideas from conformal field theory, from the very early days of the string theory, when Polyakov developed his approach to the string theory, and Liouville equation played the role of conformal anomaly in Polyakov's approach. And this is a byproduct, and this can be stated pure mathematically. So, and then another interesting space is a Schottky space. You consider the opposite case. You consider compact Riemann surfaces. Then, of course, the Schottky, the modular space MG, has a universal cover, Teichmüller space, but it has an intermediate cover, which is also very interesting. This is the Schottky space. This is which is obtained by the Schottky uniformization. So we'll discuss it in a second. And then I just mentioned this in passing, although this may be the most important thing, that Weil-Petersen metric is natural on the modular space of compact Riemann surfaces, but it's not the final. There is the final metric on the modular space which has this form. It belongs to the same Kähler class as a multiple of the Weil-Petersen metric. H bar is a positive number, plus there is an infinite sum of del bar exact terms. I put it in quotes, unquotes, because this is only an asymptotic expansion. The metric itself is not known. And this metric is obtained as a partition function for the quantum Liouville theory. And this is the expansion of the partition function in terms of the formal power series. So that's the first open question, which is really fundamental. Understand this quantum metric. It starts from the Weil-Petersen, and then belongs to the same class with arbitrary coefficient, and all these terms can be computed explicitly. And each of them is a nice, exact 1-1 form on the modular space. This is fundamental. It's a partition function of the quantum Liouville theory. So it depends on the theory. And quantum Liouville theory is the only theory which uses the Riemann surface data and nothing else. So in this sense, it's canonical. It's not unique. There are many other metrics, but this is the metric. We are not discussing it. I just put it as a side remark. Now this is really a fundamental thing. So, and to say last about this, this metric can be obtained, just let me say something very cryptic. This can be obtained as a two-point correlation functions of the stress energy tensor and its complex conjugate. So that's what it is. And its scalar potential is the partition function of the quantum Liouville theory. And the fact that this metric has a Kähler potential is equivalent to the fact that you have conformal word identities, which reflect the symmetry of the quantum theory. So that's all hidden in this single formula. So that's the Weil-Petersen metric. Now let's discuss another Kähler metric, which makes sense only when you have punctured Riemann surfaces. So in the remainder of this talk, we'll be discussing this part. But first, let me elaborate on Liouville action. Since Liouville action will play some role in this talk, let me remind you the explicit construction of the Liouville action on the configuration space of endpoints and on the Schottky space of compact Riemann surface. So, classical Liouville action on the configuration space. So, we'll write the equation. You consider just the simplest Riemann surface, Riemann sphere with endpoints removed. They are always normalized in this way, and then you consider the equation for the hyperbolic metric. This is called Liouville equation, and that's why the name Liouville appears everywhere. So that's very basic equation, and the fact that this metric is complete on X means that at the when you approach the punctures, the metric has the following asymptotics. It was studied, of course, the existence of such metric follows from the uniformization theorem, but actually Picard and Poincaré were proving uniformization theory by solving this equation, because existence of such a function phi on a Riemann surface X with this asymptotic behavior is equivalent to the Fuchsian uniformization of a Riemann surface X. Now then, the classical Liouville action is basically the Dirichlet functional, written here, which is divergent. Therefore, you cut small disks around the marked points, around the punctures and around infinity, remove them, and then subtract the divergence, which has this form, and then the remainder has a finite limit. This is the classical Liouville action. It's classical, meaning it's evaluated on the classical solution, on the solution on this equation. In fact, you can think of this as a functional of any collection of functions phi with this asymptotic behavior. Then it will be a Liouville action functional. Evaluated on a solution, this becomes a function on a configuration space. So this is the way of getting well-defined function on the simplest modular space, configuration space of endpoints. Then one can prove two simple facts, which follows. One says that Ci, accessory parameters of the Fuchsian uniformization, can be obtained as a partial derivatives of this metric, and the other is that basically negative S is the Kähler potential of the Weil-Petersen metric. This is a very old. I just mentioned these results because I realized that actually they were reported once or twice at the math conferences actually. But it's kind of interesting that I managed to tell these results to Beers and Alfors separately. So this was, but it was long ago. And now, and then I realized we never discussed this result. So that's the statement. Now, and so basically this, in a sense, well, quote unquote, this gives a solution to the uniformization problem, in a sense. Because what are the CIs? CIs are coefficients in a second order Fuchsian differential equation whose monodromy group is the Fuchsian group uniformizing the Riemann surface. And then the question posed by Poincaré was the following: given marked points, find CI with this property. That's the answer. Of course, it's a cheating, since in order to find this function S, you need to solve this equation, which already amounts to the uniformization. But the point is that these accessory parameters have a lot of symmetry hidden in this formula. So that's the meaning. And of course, the second equation also, so this is pure classical. This relates classical objects like Liouville equation with Weil-Petersen geometry of the simplest moduli space. So that's the... Now another construction. Oh, okay, so first now let's see how to come from the configuration space to the actual modular space of rational curves. So consider the modular space, which is essentially just the quotient of the configuration space by the symmetric group action. Symmetric groups acts on configuration space, permuting points and normalizing them back again. So there is the action. Then it's very easy to see, it's kind of nice, that's what was done by Zogrov long ago, that you can consider the following one cocycles for the symmetric group. And then, so for each I, from 1 to n, each I corresponds to a puncture. You have the one cocycle defined on these permutations, because the only non-trivial thing is when you permute infinity with one of the other marked points. Because if you permute points W1 and W2, nothing changes. But because of the normalization of the last n minus 3 points, the Liouville action is not invariant. And it's very easy to see that in fact the exponent of the Liouville action divided by pi is in fact a Hermitian metric in the holomorphic line bundle over the modular space, where this line bundle is analog of the Hodge line bundle for the compact case. And since we don't have a billion differentials in this case, this bundle is defined by the one cocycle. You consider the product of this. For each puncture you have a cocycle fi. The product is a one cocycle f. And then you consider a trivial vector bundle, line bundle over W. And then you consider a quotient by identifying this. So effectively, all line bundles on. So you obtain this line bundle, analog of the Hodge line bundle of the modular space, by taking a quotient of trivial line bundle over W with this one cocycle by this rule. So you identify points, you permute points, and you identify in this fashion. And then the fact that Liouville action is a Kähler potential for the Weil-Petersen metric on the configuration space simply says that you consider this line bundle, Hermitian line bundle, its first Chern form is a Weil-Petersen metric. So that's the metric description of the Weil-Petersen metric. So Weil-Petersen metric appears as a curvature form of an explicit line bundle.
Is it necessary to fix the last 3 points?
It's necessary because otherwise you have a Möbius group action. There is a group action. So then it's
harder to...
No, you need to define it uniquely. So Riemann surfaces, if you don't fix the points, they are equivalent. So you need to take a quotient anyway. And that's the way of taking a quotient. So it becomes a modular space.
The curvature would be otherwise be degenerate in these directions.
Yes, it will be 0. Now, the same works for I'm reviewing construction for the classical Liouville action on the Schottky space. which is also kind of interesting, since this space is really intermediate. It's not used much, although in the old days there were two very specific cases. One, well, like in the classic literature, one was the Fuchsian uniformization, which was another, which was even before, was the Schottky uniformization, because the Schottky uniformization is the most natural one. You effectively cut your Riemann surface along the cycles, and then you get a cover of a Riemann surface which is a plane domain with 2G holes, and that's the kind of the minimal cover with a single global coordinate. You have a maximal cover which is Lobachevsky plane, but that's the universal cover. Then you want to go down as much as possible. On the Riemann surface itself there is no single global coordinate, but on this cover with domain of discontinuity omega there is a single global coordinate, so it looks like this, the same W as in the case of Riemann sphere without few points. So that's the formal definition. We start with a marked normalized Schottky group of rank G. Schottky group is a free group with finitely many G free generators. This group is loxodromic, means it has no torsion, and all elements. And normalized means that you have a freedom, you have a Möbius conjugation. You choose your generator such that the first one has attracting and repelling points 0 and infinity. The second one has, say, attracting fixed point 1. This is a normalization. And the group is marked, meaning you choose a system of free generators up to a conjugation which gets eliminated by a normalization. So that's analog of, and then the space, the set of all marked normalized Schottky groups of rank G is the Schottky space. The Schottky space SG, which is a nice complex manifold of dimension 3G minus 3. It's not a cell, it has some homology, but it's very simple. It's kind of nice. And then so if you're given a Schottky group, it has a marked Schottky group. It has a fundamental domain which can be always chosen such that the boundary consists of 2G Jordan curves which are identified pairwise. Minus means negative orientation, and then effectively that's for each marked group you have this choice of fundamental domain. Then on omega is a domain of discontinuity. It's the whole complex plane minus the limit set, and then the corresponding quotient is a compact Riemann surface X. And conversely, that's the Schottky theorem, which is called classical retrosection theorem, that every compact Riemann surface can be represented in such a way for some sigma and omega. And let me point here that this in classical Schottky groups are such when these curves can be made Euclidean circles. But there are also non-classical Schottky groups. So to cover the whole Schottky space, one needs to consider arbitrary. They could be really Jordan curves and cannot be made into Euclidean circles. And then one defines the classical Liouville action by the same formula as Dirichlet functional, but there is some very interesting problem which can be addressed in two ways. So you see here, phi is not you can consider the first term, which is the integral over the fundamental domain, but this term is no longer invariant in a sense that if you replace fundamental domain D by another fundamental domain, this integral changes because phi is not a function on domain of discontinuity. Why? Because the Schottky group acts on the omega, and therefore phi transforms. And therefore, to make it invariant, to make this function, to make S to be an actual function on a Schottky space, and to make it, to define it in such a way that it is independent on the choice of the fundamental domain, then one needs to add a certain collection of line integrals, which are defined explicitly here. This looks a little bit complicated, but there is a very general machinery which lies behind such formulas. Namely, you can consider you need to make everything proper. You need to consider, like, we have a domain with the group action, and therefore, in order to define integration, one needs to consider double complexes. For instance, in cohomology, one needs to consider differential forms, tensor with the bar complex, bar resolution complex for the group. And then you can track different choices of fundamental domains, how they reflect. And therefore, this, what's written here, is the result of evaluation of a total cocycle in this complex, which I am not defining, over total two-cycle. And therefore, by this machinery, this is well defined, doesn't depend on the choice of a fundamental domain, and defines a function on a Schottky space. This is the general cohomological construction which was done there, and this works for almost for any Kleinian group. When you have this way, that's the proper way of defining integrals of, to make it long story short, this, what stands here, this part, Dirichlet functional, that is Dirichlet term, is not a 1-1 form on omega with respect to the Schottky group. In order to make it a 1-1 form, you need to consider a total cocycle. And then you need to integrate it over total cycle. And total cycle consists of fundamental domain, parts of its boundary, and so on. And that's precise evaluation map. And then one can prove same results as for the punctured case, namely that S is a Kähler potential of the Weil-Peterson metric on a Schottky space. So on a Schottky space, Weil-Peterson class is 0, and there is a global potential. And then if you take the first derivative, then it's also some classical thing, namely we have each uniformization of a Riemann surface gives the choice, defines the projective connection. And then you consider projective connection defined by a Fuchsian uniformization, which was discussed before, and projective connection defined by the Schottky uniformization. When the surface varies, this difference defines a 1-0 form on the modular space. And then the statement is that you take D of S. This is 1-0 component of Durand differential on Schottky, and this is precisely the difference between Fuchsian and Schottky uniformization of Riemann surfaces. This can be done for any. You can compare Fuchsian uniformization with any. You can consider quasi-Fuchsian, can consider Kleinian, and this similar formula holds. So that's the old story. Now let's discuss something. Let's discuss the new type of a metric. Well, not really very new, but let's consider the case when Riemann surface has punctures. So we consider now the case when Riemann surface X is uniformized by the Fuchsian group of type Gn. N is strictly positive. And so let's consider complete set of non-equivalent cusps. So then we have a hyperbolic plane. The group has n parabolic generators. So they have fixed points, cusps. One of them is infinity. So these are parabolic generators. You consider the cyclic subgroups generated by them, and then normalize. So each cusp by conjugation can be moved to infinity, and so you introduce these elements sigma I, such that conjugacy class of Si is a standard parabolic generator which fixes infinity. And then the next ingredient looks, well, it's very natural for this setup, but for the metric geometry of modular spaces looks rather mysterious. In this situation, let's consider Eisenstein mass series, which are defined by this absolutely convergent series for real part S greater than 1. Here gamma runs over all coset space, little gamma over the gamma I, and then you take imaginary part of this. This is very easy to see that this is absolutely convergent. And the Eisenstein mass series are fundamental objects. Namely, they satisfy Laplace equation for any value of S, where delta is Laplace-Beltrami operator on Lobachevsky plane in hyperbolic metric. And then, of course, they appear as a fundamental ingredient in many constructions. When real part S is 1/2, first of all, this Eisenstein mass series can be continued meromorphically to the whole complex S plane. On a line real S equals to 1/2, they are regular, and they constitute the complete set of eigenfunctions of a continuous spectrum. You have a spectral decomposition. They possess a lot of fundamental properties, and they also have some mysterious properties. But here in this setup, something much simpler appears. We consider this Eisenstein mass series when S is simply equals to 2. So we consider them in the domain of the absolute convergence. So all I said before is just for the information. That's not what we are using. But the fact, so they appear. And then the fact is the following, that using this Eisenstein mass series at S equals to 2, this 2 stands for number 2, one can define the inner products which look like Peterson inner product with additional weight. Since this Eisenstein mass series are automorphic, gamma automorphic, you can add them as a factor. Note that when real S is greater than, when S equals to 2, each term in this series is positive. Therefore, this is strictly positive. And therefore, these inner products define Hermitian metrics on the Teichmüller space. Now, it's a Teichmüller space because we fix the puncture with number I. I puncture is fixed. So they define. Then, of course, if you take the average, then the resulting series is, the resulting sum is modular invariant, and then this is, and each of this, in fact, is a Kähler metric on the Teichmüller space. The sum projects to the Kähler metric on the modular space. That's what basically we found out with Zograf. Then this was studied by Lin-Wang, by Scott Wolpert. Then this cusp metric is not complete. Cuneo, Abitsu proved this. And there are many, and we'll discuss some of the things. But now the open questions. What are the curvature properties of this metric? Not clear. And the reason is rather deep. Because for Weil-Petersen metric, the curvature properties for Weil-Petersen metric follow from the fact that there is a nice choice of geodesic coordinates, Beer's coordinates, when roughly all Christoffel vanishes. So this is Riemann normal coordinates. And then computation becomes manageable. First, they were done by Alfors using multiple singular integrals. Then Scott Wolpert did them nicely using Green's functions. So this is unknown. Now, using what are the corresponding volumes of the modular space using these metrics? Because we know that Weil-Petersen volumes of the modular space play a very important role in Gromov-Witten theory, in enumerative geometry, and in the work of Manin, Zagier, Zograf, and others. And so, is it possible to find this? So these are two interesting open questions. And now, let me say a little bit about this value S equals to 2. This value 2 sounds mysterious, kind of strange, because why you have this particular value? But in fact, again, this value s equals to 2 is fundamental. And so let me write down, because it's in fact this value s equals to 2, and this equation written here, when you plug in s equals to 2, you get negative 2 here. This is in fact a linearized version of the Liouville equation. So s equals to 2 plays a fundamental role. If you write the Liouville equation, and then let's represent phi in this form. The classical solution plus t something small. Suppose t is rather small. Then this linear term will satisfy the following equation. And this is precisely, if you move this here, put a negative sign, and remember that Laplacian in xy is 1/4 of this, you get precisely this equation. So the special value s equals to 2 is really special. This is related to the hyperbolic geometry of the underlying Riemann surface. So that's the explanation. And of course, these things appear also implicitly. Eisenstein-Maas series appear in Wolpert's formula for the second variation of the hyperbolic metric, and so on. So this is really a fundamental object. And now let's discuss potentials for this matrix on the configuration space first. And then so let's consider another classical object, Klein's Hauptmodule. Hauptmodule is essentially the function which describes the covering of your genus 0 Riemann surface by the hyperbolic plane. Or in classical terminology, Hauptmodule is a function on the upper half plane which is gamma invariant and such that on each fundamental domain it takes its every value 1. It's a Schlicht function on them. And then as such, this function has Fourier expansion at the cusps in the same form, where sigma I and sigma n are same as before. They used to normalize cusps, used to send cusps to infinity. And then it's a very simple, although kind of statement, that this cusp matrix, they're Kähler matrix, and they have global Kähler potential on the configuration space of n points, and this global Kähler potential are given by the absolute value square of the first Fourier coefficient. This function is Schlicht, therefore first Fourier coefficients are non-zero, and their modulus square are positive, therefore the logs are well defined. Then these functions can be also explicitly described in terms of the hyperbolic metric by using these asymptotics that I discussed. Then this function by this formula. Then also there are another interesting ingredient is the following. Let's consider this Hauptmodule J. And then essentially its Schwarzian derivative appears the corresponding Fuchsian equation, which uniformizes the underlying Riemann surface, uses Schwarzian derivative of the Klein's Hauptmodule. This Schwarzian derivative is a rational function, or rather, if you project this Schwarzian derivative of this Schwarzian derivative is a regular automorphic form of weight 4. As such, the space of all automorphic form of weight 4 is a direct sum of the Eisenstein series and cusp forms. Then, if you consider projection of this form on the subspace of cusp forms, you get, for each Riemann surface, you get a family of cusp forms which define a 1-0 form on the modular space. And then this, if you consider Liouville action on genus 0 and add this global potential for the cusp metric, you get another function on the configuration space such that its second derivative measures the difference between Val-Petersen and the cusp metric, and first derivative gives exactly the projection of S onto the space of cusp form. So this answers another simple classical question. When you consider Fuchsian differential equation, it has second order poles and first order poles. You can convert first order poles into the sum of holomorphic of quadratic differentials, but then which project on, which become cusp forms. But the sum of the second order poles contains Eisenstein series, but doesn't lie completely in the subspace of the Eisenstein series. There is an interplay between Eisenstein series, holomorphic Eisenstein series, and cusp forms. This interplay is exactly captured by this. So if you project Liouville action, you get cusp forms, but some of the cusp forms will be missing. This extra term gives you precise projection of S onto the subspace of the cusp forms. Then this can be, as before, this can be casted into computation of Chern forms. So remember, we define this one cocycles Fi. Then they define each of these cocycles define a holomorphic line bundle lambda 0I on the modular space M0n, so that the Hodge bundle is the tensor product. Then each of these Hi determines Hermitian metric in these line bundles, and the first Chern forms are given by this formula. This is precise specialization of Hermitian metric that Scott Wolpert did in 2007. That's the explicit expression in terms of the Klein-Haupt module of the cusp metric. Also, Lin Wang introduced something similar before, but this was explicit. And then another ingredient that we consider, since the Hodge bundle is a tensor product, the ratio is a trivial bundle, and therefore the function S, curly S, defined here, is invariant with respect to the symmetric group. Therefore, on the modular space of genus 0 Riemann surfaces, Val-Petersen class is the same as cusp class with this multiple. Now let's consider another space, the Schottky space with marked points. Schottky groups are by definition loxodromic, so we cannot add parabolic elements to Schottky group. But instead, you consider the holomorphic fibration. You take the classical Schottky space and consider fibration such that each fiber over each is a configuration space of n points on Schottky domain. Specifically, if sigma is a marked normalized Schottky group with domain of discontinuity, then the fiber is precisely configuration space of n points in corresponding Riemann surface. And then you can play the following. You can compare now Fuchsian uniformization of a Riemann surface with puncture. You can have three things. You have a compact Riemann surface X, which you uniformize by a Schottky group. Then you make a choice of marked points, consider Riemann surface with punctures, uniformize it with a Fuchsian group with parabolic elements. Now let's compare the two. The comparison is that you can recover the underlying Riemann surface X from the Fuchsian group by by adding the boundary to the hyperbolic plane. You consider H star be the union of hyperbolic plane and all cusps for gamma. Then this is then on H bar the Fuchsian group gamma acts, and the quotient now H bar over gamma is a compact Riemann surface. So we have a uniformization of a compact and non-compact Riemann surface by the same group with parabolic generators. And using this, one can compare Fuchsian and Schottky uniformization by considering this covering map. Now you take a Schottky domain and you cover it not by H but by H star. And so this J is the analog of a Klein-Haupt module. But now it's equivariant, because if you act it composite with gamma, then you need to post-compose it with sigma. So this is the equivariant map of two domains where the groups act. And then the image of cusps is the orbit of the marked point. So that's the way of introducing marked points on a Schottky space. And then one can consider complete set of cusps. One can expand, Fourier expand the analog of Klein's Haupt module, consider the hyperbolic metric not on Schottky domain, but on a Schottky domain with points removed, which should be complete, meaning it should be singular at the marked points. Then you define the regularized classical Liouville action, where you take the action for Schottky, which was described before, and you basically truncate the fundamental domain by removing small Euclidean disks around these marked points. Then this action defines a function on this Schottky space, and actually this then you consider this action, and then actually this action S is no longer a function on a Schottky space, but in fact it determines a Hermitian metric on the following line bundle. You consider tautological line bundles over the modular space, tautological line bundle Li, tautological line bundle Ci over the modular space is very simple. You take an underlying element in the Riemann surface, and its fiber is the cotangent line at these marked points. And you take pullback of this line bundles to the Schottky space. Then you consider these first Fourier coefficients. They are no longer a function on Schottky space, but in fact each of them is a Hermitian metric on the tautological line bundle. The Liouville action is a Hermitian metric on the line bundle, which is a product of tautological line bundles. And then, as before, you compute the curvatures. So then the curvature of Val-Petersen form is the first Chern form for this line bundle, the same with the cusp matrix. Then the special combination has a global potential and given by this form, and this is precisely this difference of two metrics is precise combination which appears in local index theorem for punctured Riemann surfaces for the weight k equals 0 or 1. And this now corresponds to the Hodge bundle lambda 1, which is trivial over the Schottky space, and therefore over the Schottky space this combination has a global potential. Therefore this difference of classes is 0 on Schottky. So that's about line bundles and Chern forms. And now let me briefly report about regularized volume. I think Colin Guillermo talked about renormalized volume last week. Frederick will talk about later. So I'll briefly state what is interesting here for the Schottky case. You consider the Schottky three-manifold. You take a Schottky group and consider corresponding hyperbolic three-manifold. Since it has renormalized volume on its own, just by considering its Schottky group. For classical, and it can be for classical Schottky group, this was first done by Krasnov, who showed that renormalized hyperbolic volume defined by truncating the corresponding hyperbolic manifold and taking the difference between the area of truncation and the volume, regularizing, subtracting divergent terms, that this is precisely gives the Liouville action. And then this was generalized. There was one technique we done with Theo. Another approach was done by Krasnov and Schlenker. Guillermo discussed this approach in detail. But what's interesting here, you can define for the same manifold M, you can define its regularized volume differently by taking into account the marked points. Namely, you choose the marked points and take the level defining function, which is when you choose phi to be hyperbolic metric, not on the domain of discontinuity of the Schottky group, but on the domain of discontinuity minus the orbit of marked points. This is omega naught. This is omega minus the orbit of the marked points. And then this truncation is kind of strange because the level surface touches the boundary, because it goes like this. And so you need to regularize the level surface as well. So that's the asymptotic, which I'll kind of, you need to regularize the level surface by taking these other points at the boundary, and then you cut small balls of this radius delta times this Fourier coefficients, and then you take the intersection of the small balls with the surface and consider the complement. So you not only regularize the volume, you regularize the area of the level surface. And once you do it, so you get another truncation of the Schottky 3 manifold. So this will be the usual one. This is the extra piece you remove. And what's important here, that this combination delta times the first Fourier coefficient is covariant, because if you change your point Wy by another point in the orbit, then delta scales in one way. Fourier coefficient scales in the opposite way. Therefore, that's the only choice to define it in invariant fashion, because I of first Fourier coefficient depends which representative we choose, but this combination doesn't. And then, as before, then you define regularized volume in this way. This is the volume minus the area minus divergent terms, extra divergent terms, minus this earlier characteristic times the usual divergence, and then this is precisely this functional curly S which we discussed. This is what essentially we're doing with Park and Lipeng Theo. Yeah. And then this can be done to quasi-Fuchsian case, giving just the similar results. And now, just to conclude, let me add another question, just open question. You see, when we define this cusp metric, we were using Eisenstein series. Eisenstein series reflect the fact that there is certain hyperbolic, that there is certain action of a Fuchsian group. So here it's important that we consider the deformation spaces of Fuchsian groups. Now, what about quasi-Fuchsian groups? Can one define that? One can consider quasi-Fuchsian groups with parabolic generators. What are and how to define the corresponding cusp metrics for these deformation spaces? And what would be their analog? What would be the metric? And probably there should be the same relation between this, that this cusp metrics should be represented by Chern forms for tautological line bundles over this deformation in modular spaces. So that's another question that is interesting. And that's it. So thank you.
question?
So for the classical Bay-Peterson metric, we know a little bit of function theory, like that the length functions are convex to the solve. Do you know any interesting convex functions or any interesting functions on space with respect to the metric, where I take into account the punctures?
No, that's very interesting. But again, everything boils down to the following question: what are good coordinates? Bear's coordinates are no good, and
So,
that's
did I understand that you know that the just harmonic Peltrami differentials are not geodesic normal coordinates?
yes,
And you don't know any other
right,
geodesic normal
right. So that's the
Yes.
open question. Actually, many people asking. Cunha Abitsu was discussing this here, and so it's very interesting question.
Other questions? Okay, well, if not, then